As we've noted already, the challenge of synthesis lies in combining the many different reactions that we know into a logical sequence to build molecules with more complex structures and more useful properties. But how can we combine all this knowledge, all these different reactions, to answer questions like this one? How would you convert this aldehyde starting material to the amide product? Or convert 1-butene to 2-butene? Or bromocyclopentane to cyclopentanone? In all these examples, we need a series of steps, and the overall route is not immediately obvious. How might we convert this starting material to cyclopentanone? Well, in the first instance, we can think about what sorts of reactions alkyl halides are likely to do. Substitution reactions come to mind, SN1, SN2, and eliminations. Elimination of HBr at the top there would give the alkene. Below that we can envisage substitution with hydroxide, cyanide, or an amine to give a range of different products. But none of these take us to our ketone. Well, not yet. The trick we need to use is to think backwards from our product as well as forwards from the starting material. So let's bring the ketone back in and think about any reactions we know that will make ketones as products. To do this, we need to introduce another type of arrow. This fat arrow is known as a retrosynthetic arrow and means literally can be made from. So the ketone, where the arrow starts, can be made from the alcohol at the head of the arrow. And now we're getting somewhere. Combining this new insight that we can make a ketone from an alcohol with our knowledge of the different things that we could make from the alkyl halide, we can develop a synthetic route from the bromide, firstly to the alcohol via a substitution reaction, and then oxidation of that alcohol using acidic dichromate to give our ketone product. And we've got there by working backwards retrosynthetically from the product as well as forwards from our starting material. Let's look at another example. Conversion of the terminal alkene 1-butene to the more substituted 2-butene product. There isn't an obvious way to do this directly in a single step, so we need to follow the same sort of process. Start by considering the sorts of reactions the starting material might undergo. Remember that as an alkene, it's electron rich and will react with electrophiles. And we know a range of different electrophilic addition reactions, including the addition of HBr, H2O with an acid catalyst, or HCl, shown in the 3 arrows here. Now again, bringing the product back in and thinking backwards from here, well, that di-substituted alkene can be made by elimination reactions. We might eliminate HBr or HCl under basic conditions, or even H2O from the central alcohol under strongly acidic conditions. Once again, our fat arrow there is showing that the alkene, where the arrow starts, can be made from these products that are at the heads of these 3 arrows. So combining the 2 halves of information, we've got a solution to our problem. An addition reaction. Let's choose HBr. You could equally use HCl or H2O. Takes us to the secondary bromide. Remember that reaction via the more stable secondary carbocation favors this product over the 1-bromo isomer. Then treatment with strong base and forcing conditions drive the elimination reaction. Using this small, sterically unencumbered base, we have a preference for the more stable, more substituted alkene. So 2-butene, our desired product. One last example for now, the question we started with, how to convert this aldehyde on the left to the amide on the right. Again, there is no single-step process that will do this for us. So we need to think on the one hand about reactions that aldehydes like to do, and on the other hand about reactions that form amides as products. Looking at the aldehyde first off, we can think of reduction to the primary alcohol using borohydride or lithium aluminium hydride. We could oxidize to the carboxylic acid, perhaps using dichromate or permanganate. Or we might think about reacting with a Grignard reagent to form a new carbon-carbon bond. Hold those thoughts for a moment and change our focus to look at the amide product. Well, what can we remember about amides, and particularly what sort of reactions will form amides? Well, we've seen various nucleophilic acyl substitution reactions with an amine nucleophile and perhaps an ester or acid chloride starting material. So bringing in our retrosynthetic arrows again, the amide can be made from the ester at the top there or the acid chloride below via different nucleophilic acyl substitution reactions. We're not quite there yet, because remember from our aldehyde we couldn't generate either of these species directly. But with a little further analysis, we can recognize that the carboxylic acid product shown in the middle there is just one step away from either the ester or the acid chloride. So again, using our retrosynthetic arrows, the acid chloride at the bottom can be made from the carboxylic acid, and likewise the methyl ester at the top there can be made from this carboxylic acid. Combining all this information together, we can think of oxidizing our aldehyde with acidic dichromate to give the carboxylic acid. Then treat that with thionyl chloride, our reagent of choice for converting carboxylic acids to acid chlorides, and then finally bring in the amine nucleophile to displace chloride and form our amide product. There are so many possibilities and so many opportunities here. The challenge of synthesis lies in combining reactions to build complexity. In the words of Robert Woodward, who was awarded the Nobel Prize in Chemistry for his many contributions to organic synthesis, there is excitement, adventure, and challenge, and there can be great art in organic synthesis. Rise to the challenge. Enjoy the adventure. These are the tools that are used to build life-saving molecules like these ones, and the next generation of world-changing molecules, whatever they turn out to be.